Hi, good evening, everyone. Welcome to week 10 problem solving session of the Theory of Computation course on NPTEL. So, this time's topic are in week 9 we began with complexity theory, right? So, what complexity theory is basically, and what solving in polynomial time means, and why it is important. What we'll do now is actually in week 10 we focus on the classes P, NP, and talk about reductions. Okay. We'll go into detail later on. We'll solve a few questions on this. But before we move on that, we shall first solve a few questions from the assignments of week 9. Okay. So, okay, here are a few questions from assignment of week 9, which I've handpicked, which seem to be on the tougher side. Okay. So, let's begin. So, this is question number 6 from assignment 9, which says, let A be a decidable language and N be a non-deterministic single tape Turing machine, okay, that decides A in linear time, order n time. Okay, n is the size of the input. Now let Tn denote the running time of the fastest deterministic single tape Turing machine D that decides A. Okay. Then which of the following is definitely true? That is what it's saying. So firstly, let's break it down. So A is a decidable language, okay, and A is decidable via uh, a non-deterministic Turing machine, okay, and let us call it M1, okay. Uh, M1 runs in order n time, linear time, okay. So this is some M1 takes an input X, okay, and M1 takes a runtime equals order n. Next, we are saying uh, fastest deterministic single tape Turing machine that decides A. Okay, A is decidable via a deterministic Turing machine. Let me call it M2. Okay, and how much time does it take? M2 runs in M2 runs in Tn time. M2 runs in T of n time. Okay, and it says which of the following are definitely true. T of n is order of 2 to the n, T of n equals order 2 to the order n, and so on. So what the idea is given a non-deterministic Turing machine that decides A, I can give a deterministic Turing machine that decides A. I can give you an equivalent deterministic Turing machine. Okay, equivalent, what I mean is it decides the same language. How does it do that? So, how does a non-deterministic Turing machine function? There lies the process. So, non-deterministic Turing machine, it makes choices which we call non-deterministic choices or guesses on the way. Okay. So suppose I say this is the working of M1. Okay. So M1 works as follows. So this is how I'll represent it. Okay. I am in a start configuration. So now my machine can move to various states, right? So I can move to various states. Okay, and what I can do is, instead of and what I can do is, I moved from this configuration to this configuration on the input. Okay, so what does the configuration look like? The configuration talks about the state we are in. Okay, the state, the head position, okay, and tape content. So my machine moves from one configuration to another configuration. But what the typical thing about a non-deterministic Turing machine is, it makes guesses on the way. It tosses coins on the way. In other words, okay. So it makes a guess whether to move on. So if the coin toss caused a 0, then it will move to this, or the coin toss caused a 1, I can move to this. Something like this. Okay. It may not toss a coin also. That is fine. It may not make any guesses. And instead, here it may make a guess. So here it did not. So in the first step, it did not make a guess. Next step, it made a guess. So there are two possibilities. It may explore the left branch or the right branch. And this is how it goes. And then it keeps making guesses on the way. And there are so many possibilities. Out of those possibilities, even if one of them is accept, it leads to a final state, one of them leads to a final state, then it is said that the entire machine actually accepts that input. Okay, that is what it means. Now, of course, what is the most amount of non-determinism that you can add? Okay, what is the biggest, what is the hardest kind of non-deterministic Turing machine you can simulate is that, let's see the worst case. Okay, let's see the worst case. Okay, in the best case, what happens is I don't have non-determinism at all. I mean, I don't make guesses on the way at all. So this is what it looks like. So this is what a deterministic machine looks like. And if I have a non-deterministic machine that runs in order and time, then it means that I have a deterministic Turing machine also that runs in order and time, because my non-deterministic machine is behaving in this way. But this is not how it may always behave, right? My machine may not always behave this way in a very deterministic fashion. It may move in a highly non-deterministic fashion, by which I mean on every on every step of the Turing machine, it's making non-deterministic guesses. And next step, and next step, and so on. Right. So this is the worst case in that sense. This is the most non-deterministic. Loosely to call it, we'll call it the most non-deterministic way a machine can behave. Now what we'll do is, the running time of the machine is how much? The running time of this machine M1 is order n. The running time of this machine is order n. So on what does it mean? It means on any non-deterministic path, M1 takes order n time. Okay. So on any non-deterministic path, this longest path from root to leaf. Okay. So my machine may work like this. It may go from this way, or it may take this way or this way. But what is the longest path possible? It is the running time of the machine, because exactly this arrows represents the steps of the Turing machine, right? Longest part of the machine will be at most order n. On any non-deterministic path, M1 takes order n time. Now, if we recall from the lectures, if I want to convert this non-deterministic Turing machine to a deterministic Turing machine, if I want to convert this non-deterministic machine to a deterministic Turing machine, what do I do is, I explore each branch. Okay, I explore each branch. I can either go in a depth first search manner, or I can go in a breadth first search manner. Both are equivalent. But in total, how many paths do I need to explore? Well, here is one path, here is another path, here is another path. So this path corresponds to all zeros. This next path, okay, first path is like all zeros, whose length is order n. Second path is first I take a 0, then I take a 1, first I take a 0, then I take a 1, then I take all zeros. And similarly, all so third path is say 0, 1, then I take a 1, then 0, 0, 0. In other words, it's all possible. Order n length binary strings. All possible order n length binary strings. Now, what does this mean? Um, how many such strings are there? How many? 2 to the order n by a simple combinatorial argument. Right. So, what does this mean? What is the key takeaway? Exploring. So, my deterministic Turing machine would look like this. Okay. So, here is my deterministic Turing machine deciding A. Okay. For each y in 0, 1 power 2 to the order n. So I'm going across each order n length binary string and simulate machine M1, that non-deterministic machine, on path y. If on a path M1 accepts, then accept. Okay. So what I'm just doing is I'm exploring all possible paths. If it accepts, then accept. And so what is the time taken by this machine? What is the time taken by this machine? So yeah, so for each of the 2 to the order n, I am taking some order n time. For each of the 2 to the order n paths, I am taking some order n time. So it's 2 to the order n times order n. Right. Now, because of order notation, we know that this is the dominant term here. Right. And I can always give another 2 to the bigger, I can always give 2 to the cn such that this is greater than 2 to the cn is greater than this term. So this or times order n does not matter much. So this is again 2 to the order n. So what does this mean? If I have the fastest Turing machine and say M2 is the fastest deterministic Turing machine, this should always be less than running time of M2 should always be at most 2 to the order n. But since we are talking about order notation, we can change it with equal to, because equal order notation already means at most. Okay. So yeah. So running time of M2 is at most 2 to the order n. Why? Because if this was not the case, okay, and let's say running time of M2 was greater than 2 to the order n. Running time of M2 was greater than 2 to the order. But then I said, okay, I gave you a Turing machine that computes the same language which takes only 2 to the order n time. And your supposedly fastest Turing machine takes more than 2 to the order n time. But how can it be faster that way? How can it be the fastest Turing machine then? Right. Oh, sorry. I don't think I can undo now. So what I'll do is, yeah, anyway. This holds. Therefore, yeah. Therefore, answer, what is the answer? So Tn takes order 2n, Tn takes 2 to the order n, tx takes so and so and so, but the answer is 2 to the order n. Answer is B. Tn takes order. This time is nothing but Tn, according to the question. Okay, good. So let's look at the next question. Question says, let primes denote the problem. Given a natural number n, output 1 if n is prime, otherwise output 0. Okay. One straightforward algorithm for primes is to check for divisibility by numbers between 2 until root n. With regard to this, select all that apply. So what it says is, so primes, okay, so primes is given a natural number n, output yes if n is prime, no if n is not prime. Output yes if n is prime, no if n is not prime. So what is the high school method of doing it? So prime, what is prime? Prime is only factors are 1 and n. Nothing between 1 and n will divide a prime number. Okay. So one possible algorithm is divide n by 2, then by 3, by 4, and so on till by n minus 1. Okay, and this is one algorithm. Another algorithm, slightly clever algorithm, is divide n by 2, by 3, by 4, and so on until by root n and then stop. Why? Because there cannot exist a factor of n which is greater than root n. There cannot exist a factor of n which is greater than root n. Why? Because if there exists because root n itself times root n is equal to n, right? And if I increase this root n plus 1 times something, then I cannot get anything else, because this needs to be very small. Whatever is here needs to be very small. It needs to be something smaller than root n, but this is not possible. Now so like for example, if I want to check whether 36 is a prime or not, I need only to check until 6. Okay, right? Oh, okay. So yeah, I'm doing this question, okay, from the past assignment, which talks about primes. Okay, so the question is, given a natural number, okay, output 1 if n is prime, otherwise output 0. One straightforward algorithm for primes is to check divisibility by numbers between 2 until root n. With regards to this, select all the options that apply. Okay. Now, primes, what is the language primes? If the input is n, then the output is yes if n is prime, or in the question it says 1 and 0. Okay. Output is 1 if it is prime, and output is 0 if n is not prime. Okay. Now, what is a prime number? A prime number is a number whose only factors are 1 and n. Okay. Now, what the question is saying is, this question is saying, what you do is you divide by 2, you divide by 3, you divide by 4 until root n. So this is a normal high school method to do it. Okay. A simpler algorithm obviously is, divide by 2, 3, 4, 5, 6, 7 until n minus 1. And if none of them divide the number, then the number is prime. But we can make the algorithm slightly more efficient by only going until root n. Okay, it takes only root n time. How you go till you divide by 2, 3, 4, and so on until you go till root n. And if root n also does not divide, then any other number after it will be a factor of one of these. So if none of these numbers actually divided number n, then obviously these multiples of 2, 3, 4 until root n will also not divide the number n, right? So that is the idea. So you go only till root n, and so this algorithm looks good, right? So the question says the algorithm performs order root n many division operation. This is true. We divide order root n many times. We are only going till root n, right? The algorithm correctly outputs if n is prime. This is also true. So because we just saw that any number that is after root n is a multiple of these, some combination of these. Okay. So so going until root n is fine. We are happy with it. So the algorithm correctly outputs if n is prime. Now, this algorithm has polynomial time complexity. Now here's the tricky part. Okay. The problem here is actually as follows. The problem or the catch. It looks like it takes polynomial time, right? It takes only order root n time. So what is order root n? Order root n divisions, right? Order root n divisions, which is order n to the half. So this is still polynomial. Actually, this is actually slightly better than polynomial in some sense. It takes only some sublinear exponent, n to the half, and this looks like it takes polynomial time. But actually, it's not taking n to the half. It's taking n to the half, capital N to the half. What does this mean? I'll tell you. This n is given as input in binary. So what does it mean? Okay. Catch is n is given in binary. So what does it mean? Number of bits to represent n is log of n. Okay. Number of bits to represent n is actually log of n many bits. So input length, that is n, okay, is actually log of n. Getting it? So, and n, like I said, n is actually log of n. So by property of log, you have that capital N is nothing but 2 to the n. So what does this mean? This is equal to order of 2 to the n by 2. Getting it? So this is the catch actually. The input given to us is given as binary. The number n, capital N, is represented in binary. If it is represented in binary, what is the length of the input? Log of capital N. If the length of the input is log of capital N, okay, length of the input is log of capital N. So what is capital N actually? 2 to the n. Okay, and the amount of the algorithm performs order root n many division operations, right? Order root n is nothing but order n to the half. Is nothing but order n to the half. But what is capital N? It's 2 to the n. So we have order 2 to the n by 2. What is this? This is exponential in n, which is the input length, which is the actual input length. Because people may this is a good exercise because people may mistake capital N to be the actual input length, but actually the input length is small n. Getting it? So this algorithm has polynomial time complexity that is clearly false. This algorithm proves that primes is in P is also false because this algorithm is actually an exponential time algorithm, which looks like a polynomial time algorithm. This high school method looks like a polynomial time algorithm, but actually it's an exponential time. So yeah. So did you get it, Akshay? I'm audible, right?
Yes, sir.
Okay. So this is fine, right?
Yes, sir.
Okay. Good. So yeah. Okay, a quick more addition to it. Actually, this in the field of complexity theory, primes. It was not clear whether primes is in P or not. People were not sure. People thought that primes is somewhere between P and NP. Some people thought that P primes is also in NP. But actually, and composite, if you try, okay, composite is an NP. And it has a nice NP characterization. And primes is in P or not. This was an open question. Oops, open question until 2006. And in 2006, this is a famous result called the AKS result, AKS primality. And A stands for Agarwal, Kayal, Saxena, Nitin Saxena, Kayal, and Manindra Agarwal. And from IIT Kanpur, okay, actually came up with this result that ES primes is in P. So this was a huge result, and this is only resolved in 2006. Okay, so uh, what the main thing is that uh, this particular high school method actually kind of gives us the misconception that primes is already in P. Okay, it can be solved in polynomial time, but actually it is not the case. It took a lot of development in mathematics and computer science to finally declare that primes is in P. And I think this won the Godel Prize in 2006 also. This result. Okay. Anyway, uh, just a quick addition. Now we'll move on. Uh, so here's another question from assignment. Okay. Select all that are correct. A language is decidable in polynomial time by a non-deterministic machine if and only if it is in NP. And if a language is verifiable by a deterministic Turing machine, if and only if it is P, and so on. Okay, let's tackle them one by one. A language is decidable in polynomial time by a non-deterministic Turing machine if and only if it's in NP. Yes, because we are talking about non-deterministic Turing machine. This is exactly the definition of the NP class. Okay, this is correct. If a language is verifiable by a deterministic Turing machine, if and only if it is in P. First of all, verifiable by a deterministic Turing machine. This does not make sense. Deterministic Turing machine taking how much time? Deterministic Turing machine taking exponential time or polynomial time or so on. It does not say. If the answer was polynomial, okay. Let's say this was polynomial. This said polynomial verifiable by a polynomial time deterministic time Turing machine, then it is in P. Then what the definition of NP is exactly this. That is, the language is verifiable by a polynomial time deterministic Turing machine. But that would mean that if this were true, then this would mean if this is true, then this would mean P equals NP. Then this would resolve the P versus NP conjecture. because the left half is definitely the definition of NP, right? So we are saying a language is in NP if and only if it is NP. So it means P equals NP. It would imply P equals NP, but that is not true. So as soon as but not that it is not true. It is not known, and it is not even given what the time is. Okay, what the time taken is, which will determine this question. So obviously this is not true. It is not known in the case of polynomial, and it is obviously false in the case of, let's say, exponential verifier and so on. Another question: let the running time of an algorithm Fn be pi n, then Fn equals order n. And so let's see this question. Okay, Fn equals pi n, floor of pi n. What is pi? Pi is some 3.1416 and so on times n, floor of that. And now what I can do is, let me look at Gn, which is 4 times n. Gn is 4 times n. Obviously, Fn is at most 4 times n, right? Which implies Fn is equal to order of n. So this is the constant, this is the function. Function is n, this is the constant. It is bounded by some upper bounded constant. Because this floor actually 3.14 will actually, even if this floor was not there, if the answer would still be the same. Even if this floor was not there, the answer would still be the same, because 3.1416 is still bounded by 4. Now that I've added the floor, I'll only get a lesser value. No, I only get a lesser value. By the floor means I'm bringing down to the nearest integer. So 3.1, the floor is 3, and 3.9, the floor is 3. But if I do 3.9 and ceil, this is called the ceiling function. If I do 3.9 and the ceiling, it means I round up to the nearest integer. Okay, the nearest integer above it is 4. So you see where the difference is. So floor will give a 3 and the ceiling will give a 4. Okay, so anyway, this is true. Now finally, the question is, there can exist functions Fn and Gn such that neither Fn is equal to order of Gn and Gn is equal to order of Fn. So this is interesting. So Fn is equal to order of Gn means, okay, in some sense it means that Gn is always growing more than Fn. Okay, so what does the graph look like if we remember, like from algorithms and so on? So this is n. So Fn and Gn is always growing more than Fn. Okay, if we plot it, Gn is always growing faster, and Gn is equal to order of Fn means Fn is always growing faster than G. Okay, now can it be that both are growing faster than each other? That is, neither Fn is equal to order Gn and Gn is equal to order Fn. Can we have something like this? It may seem kind of absurd, right? Something like that should not happen, we would think. But we can actually construct a function that actually satisfies this. The idea is as follows. We want the function to be constantly changing in its behavior. We want Fn, Gn, Fn, and then Fn grows. sorry, Gn grows. At this point, Gn grows faster than Fn. Then this. Now Fn is growing, Gn is getting lowered, and so on. So this is the idea that we would want to construct. We can simply do the following. If so, 1, 2, 3, 4, 5, and so on. So this is n. So we notice that whenever we can construct a function, whenever that n is even, n is 2, 4, and so on, Fn is always above Gn. Okay, and if n is lower, n is odd, for example 1, 3, 5, and so on, there Fn is always lower than Gn. So this is the idea. So here we can define Fn as to be equal to, say, n, okay, when n is even, okay, and n minus 1 when n is odd, and Gn is n minus 1 when n is even, and n when n is odd. Correct? So whenever n is at even intervals 2, 4, 6, and so on, f will always be above Gn. So here what do you see? Okay, above Gn, and if it is odd, then f will always be below Gn. So you can never characterize it with this order notation. You can never say that, oh, f is equal to Gn. We can never say this, that uh, f equals order Gn, meaning that Gn will forever and ever be above Fn. You cannot say, because f and Gn are changing positions, and you cannot say Gn is equal to order Fn. That means Fn is always growing above Gn after some point. You can never say that, because again, here it is constantly changing. So this is an example of two functions that you can never put in this basket. Fn is equal to order Gn and Gn is equal to order Fn. Both of them cannot be true. Okay. So this is correct. So another nice, by a small change you can do this, but you can say like, see, sir, this kind of function we cannot never even hope to characterize it by order notation. No? So both of these cannot happen. So can you, because each of them are growing, decreasing, and so on. So question is, can you make a function that is always growing and yet this property holds? So that is an exercise I would like to give you. The answer is yes. Okay, and you can try it yourself. I'll show you diagrammatically. You want to do something like this. As you can see, the function is constantly growing also. Okay, and it is, uh, above and below each other each time also. So it's a hybrid of growing function and this kind of idea, this flipping kind of idea. Okay, yeah. So that's the end of question 9. So any questions? Is this clear?
Yes, sir.
Okay, let me know if there are any questions. Okay. Right. So here's another question. This is the last question from the assignment. The class P of languages is closed under which of the following operations? Select all that are correct. Now this is quite simple actually. Okay. So take any two languages, A is in P and B is in P. So what does it mean that A is in P? A is decided by polynomial time deterministic Turing machine MA. Let me call it MA. Okay. And B is decided by polytime deterministic Turing machine MB. Okay, MA, the language of MA is A and language of MB is B, and each of them take polynomial time and they are deterministic. They are not non-deterministic. So the question is the union of these languages, is A union B? Is this in P? Answer is yes. Okay, so I'll call it M Turing machine M A union B. Okay, what I'll do is, what is A union B? A union B means all the x such that x in A or x in B. So what I can do, I can first check whether it's in A and then check whether it's in B. If in either case, okay, run input is x, okay, run MA on x. If it accepts, then accept. If no, then run MB on x. If it accepts, then accept. Otherwise, reject. So if it is in A, then it will be accepted here. If it is in B, it will be accepted here. If it is in neither, then it will not be accepted. But anyway, A union B will not contain those kind of strings. Right. So and this guy takes polynomial time on n, and this guy also takes polynomial time on n. Total polynomial plus polynomial is always a polynomial, so it will only take polynomial time. So total it will take polynomial time, and this is a deterministic simulation. So A union B is in P. Next is A intersection B. What is A intersection B? All the strings that are in A as well as in B and in B. So what does the Turing machine look like? The Turing machine M A intersection B on input X. It's simple, it's similar. Okay. We run on A. If it accepts, then we'll run on B also, and if it accepts, then I'll accept. Anyway, because it needs to go through both the checks. So run M A on X. If it accepts, then run MB on X. If it accepts, then accept X. Otherwise, reject. Because of the fact that it needs to be both in A and B, it needs to be accepted by both machines MA and MB. So this guy takes polynomial time, and this guy also takes polynomial time. So total will take polynomial time. It's in P. It is decided. It is in the class P. Concatenation is the same approach. Concatenation. So A concat B is xy such that x is in A, y is in B. So here it's slightly more or x. Okay, wait. I'll write it as x equals uv such that u is in A, v is in B. It's a concatenation of two languages, right? Two strings in different languages. Now here, now the concatenation could have happened at any point. Say 0, 1, 1, 0, 1, 0. Say 0, 1, 1 belongs to A and 0, 1, 0 belongs to B. So this should be accepted in A concat B, but we don't know where to draw the line. Okay, we don't know. We need to, then what do we need to do? We need to check whether this is in A, this is in B. This is in A, this part is in B. This is in A, this part is in B. This is in A, and this part is in B, and so on. I won't write the algorithm, might get a bit complicated, but the idea is that if you have X, okay, then I'll check whether this part is in A and this part is in B. Then I'll check whether this part is in A and this part is in B. Then I'll check whether this part is it. So how many parts do I need to check? I need to check 1, n minus 1, 2, n minus 2, and so on. I need to check x1 to x x1 and x2 so on till xn minus 1, and x1 x2 x2 x3 till n minus xn minus 1, x1 x2 x3 x4 till xn minus 1, and check whether this is in A and this is in B, this is in A, this is in oops, this god okay, this is in A, this is in B, this is in A, this is in B. I need to keep checking. And if it so happens that in both the cases that is in A and it is in B, it means it is a concatenation of two strings that are in A and B, and therefore it should be accepted. But how many times do I need to do this? I need to do it only n many times, right? How many times? N times. Because first I need to check for x1, then x1, x2, then x1, x3, and so on till x1 till xn minus 1 x. So it's not n times, it's n minus 1 times. And each of these n minus 1 times I'm running machine A to check whether it's in A, I'm running machine MA, and to check whether it's in B, I'm running machine MB. Right. So I'm doing n minus 1 times. What am I doing? I'm running machine A, time taken by machine A, plus time taken by machine B. Which is some n minus 1 times polynomial, which is also polynomial. Right? So this also takes polynomial time. And complement is even simpler. Complement is much simpler. Complement just what you do is you just simply run the machine A, and if it says yes, say no. If it says no, then say yes. The time taken is only polynomial, right? Because you are running the machine once, and you're not doing any extra function. The yes and no will only take some constant time, and so complement will also be there. So this means that the class P is closed under union, intersection, complement, and concatenation. Okay. So clear, right?
Yes, sir.
Okay. Okay, good. Now let's move on to this week's topic. So yeah, I have a few questions here. So define the class copy as follows. Okay. Copy is just the set of complements that of the languages that are in P. It is the set of all languages such that its complement is in P. Question is P in copy? Okay, I just realized that the answer is in the previous question that we solved. Okay. The question is P equal to copy? But what does it mean that P is equal to copy? Let's look at that. Okay. That is P is contained in copy and copy is contained in P. This is the question. This is the meaning. Okay. So what I mean by this is if I have a machine for P, okay, or in other words, I have this set of languages such that L is decidable in polynomial time, then I can decide in copy also. So, which means that the complements, okay, the complements of these languages are also in P, and we've already seen that that is true. But I'll explain it again. Okay, I'll this all these terms seems kind of difficult. Okay, but what it actually means is, let's look at this. Is copy contained in P? What is copy? All the languages such that L bar is contained in P. Now, what does it mean to say that it is contained? Copy is contained in P. It means that all this entire set is contained in P. If it means this entire set is contained in P, it means each of the languages is in P. So what does this mean? This means L bar is in P, then L is in P. This is what the statement would mean. Similarly, if you look at this, okay, if you look at this, copy, you want to show that P is contained in L such that L bar is in P. Okay, which means that uh, any language in P, okay, what is this P? L such that L is in P, right? Any language in P, and we are saying both of these are equal. Both these left hand side and right hand side are equal, which means that any L here, its complement is also in P, which means L is in P, then L bar is in copy. Oh, yeah, L bar is in P, or L is in P means that L is in copy, which means that L bar is in P. Together, what does it mean? L is in P if and only if L bar is in P. Is this correct? Answer is yes. This is true. Why? This is this part of this question. P is closed under complementation. Okay. This is true. Why? Because if L is in P, then there exists a deterministic Turing machine, polytime Turing machine. Okay. And if I want to decide L bar, L complement, okay, all I need to do is run machine M. If it says yes, then I give a no. If it says no, then I give a yes. And this procedure takes polynomial time. So even the complement I can decide in P. If the complement I can decide in P, it is contained in copy, right? And therefore, copy is exactly the languages whose complement can be decided in P. And therefore, P is equal to copy. Okay.
Yes, sir.
Okay. Good. Now, yeah, here is a nice warm up on P and P and so on. So the question says, it is known that every language in P belongs to NP. Okay. Okay. So which of the following are true? That is a question. So statement 1 says it is known that every language in P belongs to NP. 2 says it is known that every language in NP belongs to P. And statement 3 says it is known that every language in NP can be decided in exponential time. So which of these are true? Let's look at the first one. Uh, every language in P belongs to NP. This is true. We know that this is true. We know that P sits inside NP. Why? Because I mean there are various ways you can explain this. One way is that P has a deterministic time Turing machine that runs in polynomial time. Okay, deterministic poly time Turing machine. Okay, M runs in okay, any language here L, okay, has a deterministic polynomial time Turing machine, and any language here L prime, okay, has a non-deterministic polynomial time Turing machine. Now, any non-deterministic Turing machine, let's say I don't make use of my non-deterministic power at all. I don't make any non-deterministic choices on the way. Okay, what is a non-determinism? Non-determinism means I have the power of guessing, right? I can move into several states, several configurations at the same time. Let's say I don't use my power, I just go one by one by one. I form a deterministic polynomial time Turing machine, right? So a deterministic Turing machine, polynomial time Turing machine is just a weaker version of non-deterministic polynomial Turing. It is still a non-determinism. It is still a non-deterministic polynomial time Turing machine where I don't use non-determinism at all. So any language in P is therefore trivially an NP that way. This is the first way to answer this question. Second way to answer this question is by the second definition of NP. Remember, NP has two definitions, two standard definitions. One is obviously it has a non-deterministic polynomial time Turing machine. The second definition is that the second definition is that um, um, uh, it can be verified in polynomial time. There is a small size certificate which can be verified in polynomial time. Okay, so that is what the second definition is, and any P language can be verified in polynomial time because you can give the input itself as a certificate. But I won't go very deep into it. Just remember this much, okay, by this trivial logic, okay, that any deterministic Turing machine is actually a non-deterministic Turing machine also, but it's slightly weaker. So statement 1 is true. True. Let's look at the other statement. It is known that every language in NP belongs to P. Now this every language in NP, that is NP is a subset of P, they are saying. But we already said that P is a subset of NP, right? Now statement 2, let's look at 2. If NP is a subset of P and it is already known that P is contained in NP, then it would mean that only this is possible, right? P is equal to N. How can two sets be subsets of each other if and only if they are equal, right? So P is equal to NP. Then this conjecture would be solved. So it is known that every language in NP belongs to P. It's not saying that it's incorrect because it may be correct. We don't know. But the fact that it is known, we are saying the statement 2 becomes false. It is not known. Not known as of now. Okay. So statement 2 is false. Finally, statement 3 says it is known that every language in NP can be decided in exponential time. This is true. We saw this already. Here in this question, it says a deterministic Turing machine takes t and time. Then there is a non-deterministic Turing machine that takes 2 to the order n time. Oh, sorry, not t and time, order n time. 2 to the order n time. So using the same simulation, okay, using this approach, that I explore every path. If instead of order n it was taking some polynomial time, then I need to explore 2 to the polynomial many paths. Okay, 2 to the polynomial many certificates, in other words, or 2 to the polynomial many paths and because it can make so many non-deterministic choices, right? I'm just exploring each one of them. I'm going brute force. How many of these paths are possible? 2 to the polynomial in our case. Here, if instead of order and add polynomial. So this takes exponential time. So statement 3. If say Turing machine name takes polynomial time, then there exists a non-deterministic Turing machine. Oh, not non-deterministic Turing machine. Oh, okay. Sorry. There exists a non-deterministic Turing machine that takes polynomial time. Sorry. I explore each path. Okay, and that takes there exists a deterministic Turing machine that takes 2 to the polynomial time, which is exponential. So this is true. Statement 3 is true. So 1 and 3 is the answer. Okay. Is this clear, Akshay?
Yes, sir.
Right? Okay. Okay. Okay, so this question I'm not doing. Okay, I forgot to include one question. Okay. I can include it right now, so no problem. But this question I'm not doing because I think you were also there when we did this, right? Finding certificates, finding small size certificates.
Yes, sir.
So it was done in the previous session. So yeah, this I'm not doing. Oh, okay. There's one important question I need to add here. Okay, but before that, I'll jump onto this question. So recall the definition of conjunctive normal form (CNF). Boolean formulas that are and of or clauses. So CNF is of this form: and of ors. For example, this is an example of a CNF. So this we did it in the lectures. Okay, and you can see that it's the same thing, right? We are doing ors first. So each of these are ors, and then we are doing ands. Right. So it can be seen as this expression can be seen as or x or y, x or z complement, and y or z. After finding this, it will be fed to the top AND gate, and we have the same expression. What is a DNF? A DMF is the opposite, disjunctive normal form. Top gate is the OR gate, and the bottom gates are the AND gates. Okay. In other words, I'll do AND first, then I'll do OR. Before we are doing OR first, then we'll do AND. Right. For example, here DNF is OR and top gate is OR, bottom gates are AND. So this expression is x and y, x and y, x and z complement, y and z. So this is DNF. Now, what do you know about these? What do you know about CNF? We know that CNFs are actually very difficult to solve. Or what do I mean by solve? I mean satisfy. Satisfy means, okay, what is meant by formula is satisfiable if and only if, okay, a formula is satisfiable if and only if there is a set of inputs x, okay, a formula f is satisfied with a set of inputs x such that f of x is equal to 1. Right. Now, we know that CNF sat which is also called SAT, okay, is very, very difficult to solve. This is NP complete. CNF SAT, which is also called SAT, is actually NP complete. Okay, and this is very difficult to solve, and it is not clear whether it is in P or not. It is in NP clearly because I can give you a short certificate. The certificate is, remember the exercise we did last time. Okay, this particular exercise. Okay, the certificate is just the set of inputs. If I give you the set of inputs, you can just do the evaluation. You can do the OR and so on, and then say, okay, yes, this input satisfies it. So therefore, the formula is in NP. Sorry, the language is in NP. So this SAT is in NP. That is easily done. Let's look at DNF SAT, a close cousin. Okay. In DNF SAT, is DNF SAT is in NP? That is the question. Answer is yes. Why is it in NP? Why is it in NP? It is in NP because I can give you a small size certificate. Certificate is nothing but the satisfying inputs. Inputs that satisfy the circuit formula, the DNF. For example, here, if I give 1 1 1 0 1 1, okay, and 1 and 1 is 1, 1 and 0 is 0, 1 sorry 1 and 0, 1 and 0 complement is 1, and this also gives 1, and the whole circuit gives 1. So this itself is a certificate. I can give you this, and you say, okay, I'll run the circuit here because it does not take much time. The entire circuit is of polynomial size, and you'll run the circuit, the formula. Sorry, I keep saying circuit. The formula on uh, the inputs, okay, and I'm getting the output of the formula as 1, which means that the circuit is satisfiable. And this is a valid certificate, right? A certificate that satisfies my formula is a valid certificate for certifying that this language, whether my formula is satisfiable or not, is in NP because of the definition of NP. Therefore, uh, if I, okay, again, to explain it, to check whether DNF or formula is satisfiable or not, it is enough for me to give you a satisfying assignment. Okay. So now this satisfying assignment I can easily give you. This is a small size certificate. What is the length of the certificate? N, which is polynomial size. Okay. Which is polynomial size. And therefore, circuit DNF SAT, okay, sorry, not DNF SAT is in NP because it follows the. Now, the question says, if yes, is DNF SAT in P? This is the question. Now let's see. Okay. Here is the formula we are given. Okay. So I ask you, give me any uh, uh, input that satisfies this formula. Give me any input that satisfies this formula. So you can give me, suppose, you say, okay, sir, 1 and 1 and 0 1 0 0 will satisfy this. And then I evaluate, okay, 1 and 1 will give 1, and then because of this OR, I'll get a 1. And someone else, okay, may also say uh, 1 and y as 1, z as 1, and the other as different, okay, so some other cases will give me 1. And I'll still say yes, that is true, because and evaluates 1 and 1 is 1, and then or, okay, as long as there is at least 1, then I'll give an output 1. So what is my observation here? My observation is, as far as I can satisfy any one of these small clauses, okay, any one of these small ands, I can satisfy the entire circuit. That is the observation here. Okay. So what I'll call each of these as are clauses. They are technically they are called as clauses. Okay. So f is of this form. X1. Okay. Clause 1 and clause 2 and clause 3 and so on. And each of the clauses are of the form x1 or x2 or x3 and so on. This is what each of the clauses are. These are called clauses. Okay, each of them are of the form ORs. My observation is that any clause satisfied, then if and only if entire formula F satisfied. Because if I satisfy a single clause, okay, then okay, what did I do? Okay, sorry. It's not a clause, it's a term. I'm sorry, really sorry. We are doing AND of ORs. We are doing OR gate at the top. So I'm not going to call it clause. These are called as terms, okay, not clauses. And these are called terms. Each of these terms, okay, if and each term is of the form x1 and x2 and x3 and so on. And if I satisfy any of these terms, my entire formula is satisfied, right? Because of the property of OR, even if one of these TIs are satisfied, then my entire formula is satisfied. So that is my aim now. I want to satisfy one of these, any one of these. So what I'll just do is, my algorithm or my deterministic polynomial time Turing machine, okay, interchangeable, is as follows. Pick a term, any term Ti, which is of the form x1, okay, I'll write it as L1 and L2 and L3 and so on. If Li equals Xi, okay, it is a positive literal, it is not negated, no negation gates, then set Yi equals 1. And if it is a negative literal, Li equals not of Xi bar, okay, then set Yi equals 0. Then my y1, y2 and so on till yn satisfies f. Okay, this is not entirely correct, okay, but what the logic was here is, I want to satisfy any of these terms. Okay, I want to satisfy any of these terms. And how do I achieve that? Well, I want to satisfy this term. What I'll do is I'll set x to 1, y is 1. Good. If I want to satisfy, say, this term, what do I do? If it is a positive literal, that is no negation gate is there, then I'll set it as 1. If it is a negative literal, that there is a not gate here, then I'll set it as 0. Then this term is satisfied. Right. That is the logic here. And what kind of terms can I not satisfy? I cannot satisfy terms as follows: x bar z. This term cannot be satisfied. Why? Because if I give x a 1 and z a 1, I need to give this a 0. Okay, but this is a problem, right? I cannot have x being 1 and 0 at the same time. I cannot have x and x being 1, both 1 and 0 at the same time. So this cannot be done. So this is a bad case, and this is what we want to avoid. So what I'll do is, okay, sorry. Finally, if there exists Li, Lj such that Li equals xi and Lj equals xi bar, if in the term both the positive and negative literals of the same variable exist, then reject. Okay, and we don't need this. Oh, not reject. Sorry. Then go to next term. If no such term, satisfiable term exists, okay, no such term exists, then reject. Okay. Otherwise, if I had found such a term where xi bar, this is not present, then I can always satisfy this term. Otherwise, accept. Getting it? So this is my final algorithm. Simply to state it, I just go across each term. I try to satisfy that term. If that term is not satisfiable, I'll move to the next term. If that term is satisfiable, then I'll simply accept. Because if I satisfy a single term, see, if there is any, okay, not clause, sorry, any term that is satisfiable, then the entire f is satisfied. Getting it? And if I don't find such a term, then I'll just reject it. Because f is not satisfiable then. Because I can never satisfy that term. Okay. Is that clear?
Yes, sir.
Okay, good. Okay, so there is one question that I want to do, that I'll quickly paste it here. Yeah. Okay, now the question is, which one do I do? Because this will take some time. Okay, so I'll do the simpler question. Okay, then we can call it a day. So this is about completeness. Okay, just a quick question. It's not too twisted. Maybe the next one It takes some time, so maybe the next one I can do next week. But here is a question. Which of the following are true about the class NP? So this is, I just want to make sure that this question is covered to understand reductions properly. Suppose A is in NP and B is NP complete, so that A reduces to B, then A is NP complete. Okay, so first, what is NP completeness? First of all, what is reduction? We say that A polynomial time many one reduces to B if there exists a transformation F such that for any X in sigma star, any input, if I want to check whether X belongs to the first language, it is as good as checking whether F of X belongs to the other language. So I'm transforming one language to another, and this is called a reduction. This F has the special property, it's called the reduction. We were doing it before in the computability section also, using that halting problem and so on. So we do this small surgery kind of thing, so that the if I have an algorithm for A, I can have an algorithm for B also. Okay, so this is what it means. Now, it means, what does this mean? If B can be solved is, oh, okay. Furthermore, F of X is computable in P by a polynomial time deterministic tuning machine. Okay. So if B can be solved in P time, deterministic polynomial time P, then what I can do is this transformation I can do it in polynomial time, right? This transformation I can do it in polynomial time, and then I can decide F of X in P time, and then that would mean that I could answer yes or no even for X, so even for A. So if B can be solved in P time, it means that A can be solved in P time. So this has been the go-to approach, okay, to check whether to resolve the P versus NP conjecture. The idea is that if I have a very difficult, the most difficult language in NP, okay, if I have a B, suppose B is the most difficult language in NP, okay, most difficult language in NP, and I show that B actually reduces to A such that A is in P, then because of this result, it means that B is in P, but since B is the most difficult language in NP, this means that P equals NP. I mean, it's kind of hand wavy, but this is the idea. So what are the most difficult languages in NP? That is the question. What is the most difficult language in NP? These are what are called NP complete languages. How are they defined? They are defined as follows. For any language L in NP, L many one reduces to B, then B is NP complete. Okay, if and only if B is NP complete. So all the languages in NP boil down to this NP complete language. Then it is called NP complete. Okay. So for example, what did we have? Example, we had SAT, vertex cover, some 3 coloring, and you saw other examples, right? So any language in NP can be converted to a version of satisfiability. It can be converted to a formula where you can check whether it's satisfiable or not. It can be converted to a graph where you can check whether it can be colored by 3 colors or not, and so on. You can transform it. Okay. Now the question is, suppose A is in NP, P is NP complete, so that A menu 1 reduces to B, then A is NP complete. Okay. That is the question. Is this true? This is not true. Because, oh yeah, sorry, this is true. Because B is NP complete. Oh, sorry, what am I saying, man? B is NP complete, and A is an NP. Okay, B is, oh yeah, B is NP complete, and A is in NP already means that A reduces to B. But this does not mean that A is NP complete, right? Because if this were true, okay, B is NP complete, A is in NP, we already know that this is there. If this were to mean that A is NP complete, then this would mean that all the languages in NP are NP complete, which is not known as of now. So this is not true. At least it is not known that it is true. Now the next question is, suppose A is in NP, B is NP complete, so that B reduces to A, then A is NP complete. B is NP complete, A is in NP, then is A in NP complete? The answer is yes, because of transitivity of reductions. Okay, because we have that, A reduces to B and B reduces to C, then A reduces to C, kind of thing. No, what we are seeing is, uh, A is in NP and B is NP complete, and B reduces to A. Okay, B reduces to, this is a standard result. Okay, this was done in the lectures. Okay. So B reduces to A, and B is NP complete. What does this mean? This means all the languages reduces to B for all Li in NP. All of them reduces to B. And now we are seeing B reduces to A. This would mean that since L1 reduces to B and B reduces to A, it means L1 reduces to A. And since L1 reduces to B and B reduces to A, it means L2 reduces to B. How am I doing this? I'm doing this because of this. A reduces to B, B reduces to C, then A reduces to C. And similarly, L2, L3 reduces to C, and sorry, what am I? Sorry. And so on. In other words, all the languages in NP reduces to A, which means A is NP complete. So this is a nice tool that is often used. And finally, if A is an NP and B is NP complete, then A reduces to B. Now, since A is an NP complete and B is NP and B is NP complete, B is NP complete already means that all the languages in NP reduces to B. And A is one such language which is an NP, and it will by definition reduce to B. So this is also true. Okay, so is this clear?
Yes, sir.
Okay, clear, right? So let me know if there are any questions. So the last question, I'll do it next week. It's a bit long. I don't think I'll be able to complete. So yeah, I'll stop it here. I'll stop the session here. Okay. So let me know if you have any questions. Otherwise, we can call it a day.
No questions.
No questions? Okay. Okay, fine. I'll stop the recording also. Okay then. Fine. Akshay.
Bye, sir.
Okay,
Good
bye.
night.
Good night.
Thank you.